Okay, so good evening. So we want to discuss this concept, permutation matching. It's actually a concept that was introduced by PM Higgins in one of his papers in 2014, where he studied this notion of permutation matching. So what I'm going to do now is to just tell you what a permutation matching is, as introduced by Higgins, and then we will also say something a little about some classes of semigroup with regard to permutation matching. So the definition of permutation matching. Let S be a regular semigroup. So one thing I have to emphasize is that this concept is defined on a regular semigroup. So the concept is not available in semigroup that are not necessarily regular. So you have to have a regular semigroup, and denote by generally in studying regular semigroups, we write V of A for the set of all inverses on element A. So we denote by this the set of all inverses. This is almost standard in the theory. Whenever you see V of A, it's denoting the set of all inverses of the element A. Set of all inverses of A in S. Inverse of an element cannot exist except if the element is regular. The regular semigroup is a semigroup where every element is regular. So every element in the semigroup must have at least one inverse. This set may not necessarily be singleton. But like if it is a group, the set is already singleton. Every set of inverses is singleton because elements have unique inverses. Okay, so a mapping F from S to S is actually a self-mapping, sending element of the semigroup to itself. It's called a permutation matching. At times we used to draw the word permutation and just refer to the mapping as a matching. If to satisfy two conditions. The first condition is to say that the map is a bijection. So it has to be a bijection, meaning it is 1, 1 and onto. And then secondly, it has to satisfy the property that for FA is in VA, for all A in the semigroup. So every element is mapped to one of its inverses. So this is what we call permutation matching. Okay? I can give you an example of what this is. For example, we can consider the semigroup T2. Remember T2? This will be the semigroup of all mappings from a set of two elements to itself. So 1, 2, 1, 1, 1, 2, 2, 2. And then it can be 1, 2, 2, 1. You have two permutations and you have this idempotent element there. You can call this alpha 1, alpha 2, alpha 3, and then alpha 4. Then we can define a map F from this semigroup to itself by sending alpha 1 to alpha 1. In fact, if you do an identity mapping, alpha 3 map to alpha 3, and you send alpha 4 likewise to alpha 4, this is like kind of identity map. this map is a permutation matching. Why? Because these elements are self-inverses. If you multiply, you see this is the inverse of itself. That is the inverse of this alpha 1 is only alpha 1 because this is a permutation. And the inverses for alpha 2 will be alpha 2 and alpha 3. You can check it, okay? By the definition of what we call inverse, inverse means the inverse of an element A, it means another element B, such that ABA is equal to A and BAB is equal to B. This is what we call inverse of an element. And this is also the set of inverses for alpha 3. And then for alpha 4, the inverse is just one inverse because this is also a permutation. So this map is actually a permutation matching. Why? Because it permutes the elements of the semi-group and it sends each element to its inverse, one of its inverse. If you pick another map, G, that will map, maybe I can write it now as alpha 1, alpha 2, alpha 3, and alpha 4, just to arrange the element. And then I say alpha 1 again, alpha 2, alpha 3, and alpha 4. And then we do like this and send alpha 2 to alpha 3, alpha 3 to alpha 2, and the alpha 1 we fix. So you see this is also another permutation of the element of T2, the element of the semi-group, and it sends each element to its inverse. The image of each element is an inverse of that particular element. So this is again another example of permutation matching. And this is also so because and now any other permutation of this set you pick apart from this identity and this particular one will end up sending some element to somewhere where it is not the inverse of the element to an element that is not necessarily the inverse of that particular element. So therefore, in other words, what I'm trying to say is that these are the only permutation matchings for this particular semigroup. So regular semigroup have things that are called permutation matchings. That is, there you can define a mapping or a permutation of the semigroup that send element to their inverses. And you can pronounce this particular condition here by saying A is equal to A, and what? FA is equal to FA. Yeah, I think this is it, because this is what defines FA to be an inverse of A. So this is what we call permutation matching. Now, with regard to some particular classes of semigroup, for example, the semigroup is an inverse semigroup. If S is an inverse semigroup, an inverse semigroup is a special class of regular semigroup in which what? In which every element has a unique inverse. So if S is an inverse semigroup, then every bijection, every bijective map F from S to S is a matching. It's a permutation matching of S. Why? No, sorry, this statement is wrong, sorry. Then it's not ever bijection. No, this statement is wrong. I don't mean, I was ahead of myself. So I'm coming to that. But for inverse semigroup, what I mean to say is that there is one and only one. One and what? And only one permutation matching. For S. for S. What does that mean? That is, there is only one permutation matching for S. This is because every element has a unique inverse. So if you see the semigroup, for example, if the semigroup is seen to be x1, x2, all the way down to xn, for example, let's say a finite inverse semigroup, one element, and you arrange the element again like this, then since there is only one inverse of x1 in this list, you have one and only one way of identifying an image under any permutation matching. So you have one and only one way of doing it. So if you map it, if this is the inverse, you can't send it any other place apart from this particular one, if we assume it's the inverse. And then if the inverse is located somewhere again, and this one is located, maybe this inverse is the inverse, and some other point will come to xn, being the inverse of that point, then you cannot change this assignment. This is the only way you can do it, given the fact that inverses are unique, and you want an element to map to its inverse. So you have one and only one way of sending elements to their inverses, since inverses are unique. So for inverse semigroup, this is the only way. Are you following?
Yes.
Yes, sir.
So this is just telling you that there are regular semigroup, namely inverse semigroup, that have unique permutation matching. But some regular semigroup may have more than one permutation matching, as we have seen in this example, where we're able to identify this permutation matching for this particular one. Okay, and then what if the semigroup is a union of groups? There are classes of semigroup, regular semigroup that are not inverse, but they are union of groups. Like which class of semigroup? Now, orthodox semigroup is not necessarily a union of group, but the class of completely regular semigroup, completely simple semigroup, or completely zero simple semigroup. Sorry. The class of completely zero simple semigroup. This will be union of groups. Because every H class is a group H class. They are idempotent everywhere in the H classes, and so therefore every H class will be a group H class. So and a semigroup can be written as the union of its H classes, given the fact that it is regular. So it has an abundant supply of idempotent. So because every H class they are idempotent, and the H class where there is an idempotent is always a group. So which means the group can be partitioned into the semi-group can be partitioned into groups, and so therefore you have a union of group. So the same thing is happening, because if you have union of group, then you have unique inverses. So actually, if the semigroup is a union, so also if S is a union of groups, then it has what? A unique matching. A unique permutation matching. Like the way it happened in with inverse semigroups. But now we define the other time the concept of rectangular band. A rectangular band is a semigroup in which every other element is an inverse of every other element. That is, we can still recall that S is a rectangular band if for all A, B in the semigroup S, A, B, A is equal to A. And this is already telling us that every element is the inverse of every other element. So what is this telling us? That for a regular semigroup, this condition is already telling us that for a regular semigroup, if I define any bijective map, no matter If you take any element A and send it to some image, whatever image you choose is already an inverse of that A. Because every other member of the semigroup is an inverse. Even A itself is the inverse of its own self. Are you following?
Yes.
So that means all the bijections from where? From the semigroup to itself are what? Permutation matchings. Yeah. Because every bijective map on S defined on the semigroup is a permutation matching. It's a permutation matching. Of S. Did you understand what I'm talking about?
Yes.
That is whatever bijective map you pick. So if you see the semigroup as I wrote there, it is a semigroup, for example, a finite semigroup of n elements, x1, x2, x3, up to xn. Then even if I send x1 to x1, it's an image. This x1 is the inverse of x. So all the elements are already inverses of this one. So I can send it anywhere. And likewise, if you take x2, you can map it anywhere. So whatever bijection you take from the semigroup to itself, it will turn out to be a matching. So how many such mappings are there for a semigroup of n elements? There will be exactly n factorial of them. So the total number of matchings will be n factorial. And you know you can compose this matching in this sense. So which means the collection of all the matchings will be isomorphic to the symmetry group. So it's a group and it will be isomorphic to the symmetry group. It could be group of permutations on n element. So there are semigroups. I'm just giving you different examples of semigroup with the permutation matches. We saw that some semigroup, some regular semigroup, like the inverse semigroup, they have only one matching, one and only one matching. And now we are seeing that every bijection between them is already a match. So this is the maximum number of matching you can get. And there are some regular semigroup with with more than one, but may not be all bijections. Like the T2 I took. If I map x alpha 1, in that T2, if I map alpha 1, for example, if I do this assignment, alpha 1, alpha 2, alpha 3, and alpha 4, and I say alpha 1 again, alpha 2, alpha 3, and alpha 4, and if I do like this, well, okay, it's alright, even if I did it like this. You see, this is a bijection. You know, it's a bijection, 1 to 1 and 1 to map. But then alpha 1 is not an inverse of alpha 2.
Yes.
Likewise, alpha 2 is not an inverse of alpha 1. So this is not a matching. Are you following?
Yes.
So since it is not a matching, it means not every bijection is a matching. So there are all sorts of things. In his paper of 2014, he actually constructed an example of a regular semigroup that don't have a single match.
Yes.
So, but I'm not going into that construction. He constructed a kind of a zero rectangular band where the matching does not exist. So you even have regular semigroup with zero matching that don't have any matching. Okay? So this is what we call matching. So actually this concept is entirely not trivial, and it is not a vague concept, in the sense that it's not a concept that is difficult to provide an example. You can see so many examples already. But there is a characterization presented there of this matching, some necessary and sufficient condition, because the problem is to find some necessary and sufficient condition under which a particular regular semigroup will have permutation matching. Well, what is the motivation for looking at this permutation matching? It's actually, it has something to do with a combinatorial problem, existence of Hall's condition for a bipartite graph. You know, because you can see this thing is like you are arranging vertices x1, x2, all the way down to xn if you think of a semi-group of n elements, and then you can duplicate, you can think of the vertices down here as even though it's still x1, x2, x3, but you can imagine it as having y1, y2, a different set of vertices, yn, and then this assignment, if it is possible, it will have something to do with a bipartite graph. You know, connecting vertices from up here and vertices down, because you have upper and lower vertices. So if the permutation matching is to exist, it has something to do with some Hall marriage condition, where you can do some assignment here. So, but I just don't want to talk about that now, since it's just to tell you what this permutation matching is. So, but the result he proved there is that, so this is a theorem, that for a finite regular semigroup, you can already notice that I was assuming n is finite, so that you'll be able to have this bijection doing what you want, control over the bijective mapping. So finite regular semigroup S. So the semigroup is regular and it's finite. Then the following conditions are equivalent. So which means each one of these conditions can imply any other one of the conditions. So to say that S has a matching, permutation matching, so actually I'm just shortening it by saying matching, a permutation matching. To say that it has a permutation matching is the same thing as saying that S is a transversal of this set. That is the set of all collection of the collection of the set of emphases as you run over. This is A. Run over the set. But what do you mean by transversal? Yeah. And also, this is equivalent to saying A is less than or equal to, that is the size of any subset A is less than or equal to the size of the set of emphases of element in that subset. Emphasis of element in the subset for all A subset of the semi. If you pick any subset of the semigroup, then the collection of emphases of that set of element should be more than, should contain more element than the element in the set itself. So at least some element of the set must have at least every element of the collection must have at least one inverse. Are you following? Because if inverses are unique, you can see this condition is already saying that if inverses are unique, then this collection will have the same size as this, as the element here. So, but it is possible that element may have, or two elements may have the same inverse. So there is a chance of having this set, even if the semigroup is regular, this set may still contain less element than the element in the set. So that situation we don't want to happen. Because if it so happened that a particular element of the set, two elements of the set A are having one inverse, one and only one inverse. That is, two elements like say x and y have as their inverses, an element z. So this has a unique inverse and it is z, and this one also has a unique inverse and it's still the same z. Okay. Then you see this set will contain less elements than here. Are you following this particular set? So in that situation, for all, because we say for all A, subset A. So if I take this particular set as my subset A, then the set of inverses of this element will just contain one element. And here, it means you have less element here than here. So the inequality will reverse. But the danger of having this kind of situation is that when it comes to doing the assignment, you have x and y here, and then along here somewhere there is z. And if you are doing matching, this x must map to its inverse. But when it comes to assigning for y, it must come to its inverse, so you must map it again to z. If you are saying every element must map to its inverse. But then in that situation, the resulting map will not be a permutation, will no longer be a permutation. And so therefore, the matching condition will not be satisfied. So you cannot have a matching if this condition is so whenever this condition happens, then you can have a matching. Otherwise, the matching will not exist. So that's why this condition is equivalent to saying the semi-group is having a matching. Okay? And then there are two more conditions, or three more. He mentioned another condition that talked about that talked about H classes. Okay? That S has a matching, that is permutation matching. That is the matching sending an element to its inverse. This kind of matching. Yeah. So, and that preserve H classes or H relation. Green's H relation. What does this mean? When you say preserving green H relation, it means if A is H related to B, then the image of A. You see, under the matching, this will be mapped to A prime. And B will also be mapped to B prime. So this will also be H related. So it should be, there is a matching that is H class preserved. So which means whenever you have a matching, then you can, even if a particular matching exists, that matching may not be H class preserving, but that is already implying that there should be a matching that preserve what H classes. And whenever you have this H class preserving matching, then automatically you have a matching. So therefore, there's nothing to prove. Automatically, this is implied. You know, because if you have a matching, you are just looking for a matching. But if you have one that is doing something particular, it's already one of the matchings you are looking for. So if you have a matching, then you can reduce the matching into a one that is what? That is preserving H classes. So this is what this last condition is saying. And then the fourth condition over here. That is the fifth condition, which is also equivalent to all of these ones, is to say that each principal factor, I don't know that you, principal factor, principal factor is he has written dA union, yeah, A in the semigroup. This is a regular semigroup already. So each principal factor has a permutation, a permutation matching. And what does this mean now? What is a principal factor? The principal factor is talking about D classes. Okay. But you know, D classes are not necessarily closed under multiplication, because at times if you take two elements of a particular D class and multiply, it will fall inside a different D class down somewhere. Like in full transformation semi-group, you can multiply element of height R, but the result may be of a lower height R plus or minus 1 or something. Are you following?
Yes.
So, but how do you make that D class? Because it's not closed, how do you make it to be closed? That particular D class is by introducing a 0 element. Okay? You adjoin a 0 to the D class, and then you multiply as you are doing in the semi-group. If the product is already there, fine and good. That means it's closed. But in the event the closure is failing, that is you multiply and it falls in a lower D class, then you now declare that product to be 0. So because you have already adjoined a 0 in the D class, then it means you are forcing every product to be closed within the D class. I hope you understand what I'm saying.
Yes.
So if you perform a product, so you adjoin a 0, and then you say two elements, you define a new operation now in the D class, A star B or X star Y, X star Y to be XY. If the product is already in that D class, okay, well, this shouldn't be call it D, and then it should be 0, otherwise that is if XY is falling out of the D class. You declare it to be 0. So for all what? For all XY in DA union 0. So even if you multiply 0 with some X, you know, the product, if you do 0 with some X, you should define it to be 0 already, because 0 is already outside. So you should understand that it's adjoining 0. When you are adjoining 0, X times 0, the center as 0 times X. Is that okay? And that is the center as 0 times 0, which is still 0. So all this will happen. So which means at all time, product will still fall inside that D class. So when you make D classes a semi-group in this way, then those D classes are called principal factors. Are you following? So like for example, if I may ask in Tn, how many principal factors are there? You have n of them. You have n of them because J1 is a principal factor, J2 is also a principal factor, J3 is a principal factor. But you should understand principal factor in the sense that you have already make it a semi-group by adjoining a 0 and extending the binary operation so that it is closed, so that if it is falling out of the class, then you declare it to be 0, so that it is closed always. And that's what we mean by principal factor. So this condition is saying that each principal factor has a matching. So which means just concentrate on the D classes. Yeah, take an arbitrary D class with the 0 adjoint. If that D class is having a matching, arbitrarily taken, then the entire semi-group is also having a matching. So just if you want to establish that Tn is having a matching for all n, just take a particular J class and adjoin a 0 with it and see it as a semi-group or sub-semi-group of the Tn with this extended multiplication as I mentioned here, and just check that that one is having a matching. You know, it's easy to do by visualizing the egg box picture. When you visualize the egg box picture, you remember Green's lemmas. The Green's lemma will provide you with a very nice way of locating where the inverses are, and then you can easily see whether the bijection is available for the J classes. And in fact, in this particular paper, that is what the author did. He actually analyzed, we say this theorem was applied to show that the full transformation semi-group Tn has a matching. He applied actually this particular theorem. So I'm explaining to you now.
Yes.
You can see that. In fact, he did it still in that paper of 2014, that Tn is having a matching. Because it's easier to concentrate in a particular J class, and it can be visualized as an egg box, and Green's lemma will allow you to identify the inverses. And so therefore you know if you pick an element where to map it. You can always find the inverse and do the mapping. So this is actually very...
So you also explain the transverse.
Yeah, this transverse, I will do it later on.
Okay.
Yeah, I will do it later on. Exactly.
The set of all
Yeah, it
inverses.
has to do with, because when you say transverse, I don't know, there are so many notions of transverse, transversal. When you say transversal, I'm thinking, do you remember in the, when you have a partitioning of a set, and then you pick an element from each class, then the resulting subset containing the same number as the classes is called the transversal of that subset. So probably, yeah, that is exactly what this is. I don't know that, even though it's not immediate to see, because I mean it's not that trivial to see that this will be S will be a transversal of this collection. When we say S is finite. That is the sense of this transversality. Okay?
Yeah.
That's the sense of this transversality. If you want me to say it again more formally, is to say that given a partition, so we say that a subset A of X, if X is a semi-group, it's a set, not an empty set, for example, a subset A of X. You see, this will be classes. Let me define it for you. Since you asked, I wanted to just leave it until later on, but what do you mean by this transversal? That is your question. So you see this this set, this is a set of subset of the semigroup.
Yes.
Set of what? Subset of the semigroup. Are you following? So what we are saying is to say that S is a transversal of this is to say that every element in S is to say that every, let me write it, element A in S belong to one and only one of these things. A is in one and only one V B, you know, for every element X it's in one and only one V, one subclass here. For some A in S. Okay, look at it now. What will be the implication, the consequence of having an element appearing in two places? That is, if a particular X is found in VA and the same X is also found in BB, what will be the implication of that? So if you are trying to map A to its inverse, you can end up mapping it to X. Okay? So what if that happened? You see, this one will eventually lead to this danger we are avoiding.
Okay.
Because what if this particular one is having, if this is singleton and X belong there, and this also singleton X belong in there, and you want to map B to its inverse, then you have this problem. If an element belongs to two different set of inverses, particular element of the semigroup, are you following?
Yeah.
Then you may end up mapping one, the two elements to that particular common element in the set of inverses. Are you following?
Yes.
So every element should appear in one and one and only one set of inverses, which means this set of inverses should form a partitioning of the sets. Are you following?
Yes.
It should form a partitioning of the sets. Because if it is a transversal, then you should have a partitioning of the set.
Okay.
So that is what this transversal is
Yeah.
talking about. But then our the sixth condition, go. So let me write the sixth condition. So the sixth condition is to say that each zero rectangular band, and then rectangular band, zero rectangular band is still coming. Rectangular band, DA unit. So if you say zero rectangular band, then you are saying that this D class is having singleton H classes.
Okay.
You know, it's an egg box.
Yeah.
So every H class is containing only one element.
Okay.
That is what is making it a zero rectangular band. Well, it is a rectangular band and it's a combinatorial semigroup, they are called. Semigroup with singleton H classes. Okay? So, but you can make even if it is not such, you can take the quotient with the H classes. You know, H classes. So every such has a matching. So, and this theorem, if well understood, can be effectively utilized to showing that if you want to show that a particular semigroup has a matching, you can effectively utilize this theorem. So you can pick any one of the six conditions that is more friendly to work with depending on the situation you are in, and utilize it to just show that the condition is satisfied, and then you can conclude that the semigroup has a matching. Okay? And it is also used to show that the full transformation, the partial transformation semigroup has a matching. So you can extend it to, in fact it has been extended in the literature. But there are some open questions here. There is the notion of a matching being an involution. Like the matchings we describe for inverse semigroup. These matchings, you know, they are unique. Now you see every element is mapped to its inverse. But the reverse, that is the inverse of that particular matching as a mapping is also sending every element to its inverse. So the inverses are also unique themselves. They are matching themselves.
Okay.
I hope it's okay. So this is so it is an involution in the sense that if you compose with itself, you still get the element back. So this is the notion of involution matching. But now the question is, Tn, you know, it has been shown that every inverse semigroup, that is completely inverse semigroup and inverse semigroup, they have involution matching. But then the question is, does Tn the full transformation semigroup has an involution matching. And how about order preserving? Whether order preserving transformation has also been shown to have a matching. All these are questions he mentioned here. And does any finite regular semigroup with a permutation matching possesses an involution matching? That is, if there is a permutation matching, can we conclude that there will also be an involution matching? So these are some of the issues. But in essence, what I wanted to just do is to tell you what a permutation matching is.
Yes.
And I think we have defined it. So you can just go through these papers and try to see how much you can understand this concept. Thank you very much.
Thank you, sir.